Okay, once again, for people who came in the last 2 or 3 minutes, the presentation I'll be speaking from is available on the Streaming Learning Center site now for download. It's in PDF format. Just click the article on the top left, scroll down a bit, and here's the PDF file. So it's available now if you want to have it to refer to when I'm talking. There's a lot of fine detail in some of the slides, so you'll probably want it if you want to look at some of the data later after the presentation. You guys ready back there? Okay, well, thank you for coming. This morning I'm going to be talking about pretty much how I use objective quality metrics in the consulting and the writing and the testing that I do for clients as well as magazines and the books that I write. I want to start with a brief overview of objective quality metrics, the tools that I use and some that I'm actually looking at now that are new. Talk a little bit about how I use the results from those tools to configure my X.264 encodes, and look at how we measure adaptive groups, choose the optimal resolution, and then end with a brief look at the computer requirements. So what are objective quality metrics? Essentially, they're mathematical formulas that attempt to predict how human eyes would rate the video. So you use objective quality metrics because you want to predict how subjective viewers would rate the videos. Some of the examples you've probably heard of are peak signal to noise ratio, structural similarity index, video quality metrics, Sim+, and there's a couple other we'll talk about in the early part of the presentation. So if you look at a subjective versus objective quality, without question, subjective quality evaluations are what we care about most. I mean, if you can get a panel of people to rate videos when you're making your configuration decisions or technology decisions, that's the absolute best way to do it. Because really, that's what you care about. You care how subjective human viewers rate the videos. The problem is, it's expensive and it's very time consuming. So if you're trying to figure out what the best keyframe interval is, you can't get 20 people in a room and look through 40 videos. So it's very difficult to do. You want to do very high level decisions, very important decisions. Next level is the golden eye. That's where you have 1 or 2 people who are very knowledgeable about the type of artifacts that are present in compressed video, and you have them look at the video and make compression decisions based upon their evaluations. And that's kind of what, I've looked at a lot of video over the days, and that's kind of where I see myself. The problem is, if you're looking at 1 or 2% difference in terms of overall quality, it's almost imperceptible. You really can't see it. So when you're making configuration decisions, it's impractical and doesn't give you the results that you want to use. And then moving into what I'm going to call perceptual quality analyzers. What these tools do, and we'll see this in more detail on the next slide, is they try and measure the actual error between the original source video and the compressed video, and then they try and evaluate that using different measures that relate to how people perceive video. So it's not just a measure of the error between the original video and the compressed video. It's a measure of how people perceive that error. And again, we'll see more about that in a second. And then the last category, or I guess in this category, are tools or metrics like PQA, which we'll see, Dimas, or difference mean opinion score, which we'll see, Sim+, which we'll see. And then Netflix released a tool, I guess in the June timeframe, called VMAF that is in this class. And then the lowest class are the math-based quality models, and that's Psnr, which is probably the most familiar, and SIM, SSIM. And what these tools do is they just measure the error, and they do very little in terms of the perceptual adjustments here and actual picture quality metrics. So if you look at the reference videos here, the test videos here, Psnr and SSIM pretty much measure the difference between the original and the compressed video. They measure the error. Now, sometimes that error could be really unimportant. I've seen very, very low Psnr scores because there was a slight shift in the tint of the video. So a viewer would look at that and they wouldn't notice it. Unless they were looking at them side by side, a small change in tint would be irrelevant. On the other hand, for Psnr, that could be a huge factor. So the pure math models don't do a good job of actually converting the mathematical results into how people actually view the videos. And as we move through these levels, we get more and more perceptual adjustment and more actual picture quality measurement. Okay, so these tools, these are the really, really high-end tools that cost a bunch of money. These are the really accessible tools. And what we're going to spend some time looking at is how much value we can get from these tools, because unless you have $19,000 to spend, you're not going to get these tools. And companies do buy them, but you know, it's certainly out of my budget. So I just wanted to, you know, again, I mentioned a second ago that the role of the objective metric is to predict subjective scores. That's why we use it. We use it not to get a number, but to say, hey, how would a human eye actually view this? And what you see a lot of times when people evaluate quality metrics is you see a graph like this. And on one axis is the score of the objective quality metric. And on the other axis is the score from human comparisons. And when you have a perfect score like this, you have a perfect correspondence between what the computer model generated and what the viewer reported. Does that make sense? So we have a perfect line here because the objective quality metrics accurately predicted the subjective score at each level. Of course, that never happens. So what you end up seeing is when vendors release their tools, they release a graph like this for their tool, and this is attention-weighted difference mean opinion score. This is the highest level objective quality metrics that Techtronic's offered. And you see there's a pretty close pattern here. It's not like what we saw in the previous slide, but it's still a whole lot better than the Psnr score, which they pretty much say is almost random. Okay? So this is what you look at when people report the accuracy of their video quality metrics. And this is a tool called Sim+. And this is the next level of the structural similarity index. And you can see they've got even a better correlation here. And again, Psnr is everybody's beat bag, you know, and everybody says we're much better than Psnr, and here's our proof. So this is kind of, you know, this kind of shows what these tools are trying to accomplish. They're trying to say, if you use our metric, you will get a high correlation between what our metric shows and how humans will perceive it. If you use Psnr, you will get a low correlation between what Psnr reports and what humans report. Okay? And then this is kind of a metrics taxonomy that I put together to cover pretty much all the metrics we're going to be looking at over the next few minutes. And then the basis is kind of goes back to this slide here. You know, is it noise computation, or does it have a lot of this refinement? So, you know, Psnr, it's pretty much mathematical error, the predictive value. You know, we've seen everybody who compares their technology to Psnr says it's almost random. Is it device specific? So if you're, you know, a video that's encoded for a cell phone looks different than it would on a 4K TV. Does your metric allow you to measure that? Yes, no. Psnr, as it relates to the Moscow University tool, does not let you measure that. So you get one score applicable for all those devices. Attention weighting. So this is a feature of the two metrics here in the Techtronics tool. And what that does is say, okay, you know, the viewer is watching here. And if there's error out here, we're not going to count it the same as error in here. So, you know, that's obviously pretty useful for almost every video that you do. And then score correlation, what I mean there is when you get a score, does that tell you how the subjective viewer will rate the video? So a Psnr score might be 42. What does that tell you about how a viewer will perceive that video? Is there a score correlation, yes or no? So MSSIM, it's a little bit more refined. Predictive value is a little bit better than Psnr in theory. Device specific, no. Attention weighting, no. Score correlation, no. And then Psnr you can get with FFmpeg. It's free. I use the Moscow University tool. You'll see why in a few moments. Sim+ has more perceptual weighting. The predictive value, again, that's the scatter graph we saw a few slides ago. They say it's very good. Is it device specific? Yes. So with Sim+, you can say, tell me how this video looks on a cell phone, but also tell me how it looks on a 4K video or a computer monitor or a TV. And that's really valuable if you're configuring your videos for these different targets. Attention weighting, no. Score correlation, yes. And we'll cover that in a moment. But if you get an an 80 to 100 score on the SQM test, they're saying viewers will rate that as subjectively excellent. If it's 60 to 80, they'll rate it as good. 40 to 60, they'll rate it as fair. So you have a good level of insight into at least how they believe those scores correlate with human subjective ratings. And these are the two Techtronic visual quality benchmarks. I have the least experience with these. I just got the tool in a couple weeks ago. Very, very fun tool, very good tool. A lot of configurability. You know, it's device specific, attention weighting, score correlation for Pqr. I'll cover how the correlation works in a moment. And then the attention weighted difference mean opinion score, that's the most advanced one yet. The problem is the tool costs 10 grand. It's 10 grand without batch encoding. So if you want a batch encoding so you don't have to wake up every 45 minutes to load another test, you got to spend another 9 grand. So it's an expensive tool. You know, you've got to be a pretty big company to access that. So what I did is I said, well, heck, I've got all these tools. Why don't we encode some files in different ways and then measure the difference in all these tools with all these metrics. So what I did is I encoded 3 files. 720p, the data rate varied per file. And then I encoded them with the baseline, main, and the high profile. This is a pretty fundamental decision you have to make in encoding H.264. Then I measured with the different tools, and we'll see how they work, and we'll draw conclusions about the comparative quality. So this is PSNR. So PSNR is higher scores are better. It's theoretically on a rating from 0 to 100. So if you have, if you have a black frame and an encoded black frame, there's no detail. You could get a theoretical 100 on that frame. You see that sometimes in fading in from black in some videos. What Netflix came out with when they issued a report on per title encoding or a blog post, and they said, we're using PSNR to compute our per title encoding, and what we found is anything above 45 is perceptibly imperceivable to viewers. So there's no sense adding data rate to go above 45 because nobody can see it. And they also said that below 35, there are almost always visual artifacts. So if I'm looking at a PSR number, if it's in the 40, 42 range, I'm thinking, okay, that's probably fine. The viewer's not going to notice any issues with that. So what are the PSNR results? Again, higher scores are better. So the talking head video, no surprise, that's the highest quality video. The haunted video it's kind of a movie-like, it's a video I produced for a haunted house, an advertising video for them. It's kind of movie-like production, a lot of different cuts, a lot of different high and low motion. And then Syntel is the Syntel animation. So we've all seen the Syntel animation from Blender on the internet. So Syntel is the lowest, talking head is the best, and we see very little meaningful difference between the 3 profiles. We see that baseline is in fact always the worst. Main is higher than baseline to a much greater degree than high improves quality over the main. Does that make sense? Okay, so this is peak signal to noise. This is multi-scale structural similarity. So this is MSSIM. And again, here the higher scores are better. Theoretical maximum of 1. And there's no interpreting the scores. You just know, if it's higher, it's better. There's no correlation between what the score is and what a user might perceive. And again, we see Syntel is by far the lowest. And we see this looks pretty significant, but the numerical difference between the 0.965 and the 0.9, or the 985 and the 0.990 is only 0.015 or 0.15, whatever. So it's not a huge difference. But again, the same thing, talking head's the best, haunted is second, Syntel's the lowest, and baseline's always the worst, main is in the middle, and high is always the best. So now we have Sim Plus. Sim Plus is the one I mentioned a few minutes ago, that anything between 80 and 100 is going to be rated excellent. Higher scores are better. Syntel, again the lowest, haunted in the middle, talking head, again the best. The difference is greatest between baseline and main is always slightly lower than high. If you were looking at these and trying to make a compression decision, you would say, well, heck, all of these are in the excellent range. So, I can use any profile with these videos, and we're not going to, the viewer won't see a difference. Okay, this is picture quality rating, the first of the Techtronics objective quality metrics. Lower scores are better. And this is kind of an interesting tool because they're using the concept here of just noticeable difference. So a Pqr rating shows you that if you have a difference of 1 in the Pqr rating, that's a difference of 1 just noticeable difference between one video and the other. And the way a just noticeable difference works is if there's only one JND between the two videos, very few people can see it. If there's a JND difference of 2, between around 90% of the viewers can distinguish between the videos. So what we're seeing here, and again, this is much greater precision, and that's what I like about the Techtronics tool. We're seeing, okay, the difference here is from 3, this again is the Sintel clip. It's the lowest quality of the 3. Baseline is again the lowest quality because lower scores are better here. And we're seeing less than a 0.5% difference on the JND scale. So what this tells us is no viewer would see the difference between the baseline and the main profile, and certainly no difference between the high and the main profile. And same thing for the two other videos. And finally, the attention-weighted Dimas. This is, I think, the most advanced algorithm Techtronics offered. Here, 0 to 100 is the scale. And they say there's very hard to draw a correlation on this because even though humans typically rank difference mean opinion scores on a scale of 0 to 100, they hardly ever rank in the 0 range because they never know if a video is going to be the absolute worst quality they're going to see because they haven't seen all the videos yet. And they never rank at the high because they haven't seen all the videos. So they never rank, they kind of compress the scores in the middle. So if you read the documents from Techtronics, they say use these to talk about the relative differences, but it's hard to draw any correlation about what a viewer would actually rate that video. On the other hand, if you look at a difference mean opinion test for humans, anything from 0 to 20 is good video. And if you look at their rating system in the tool, anything in the 0 to 20 range is green, which would tell you that that video is probably pretty high quality. So I think they're saying, again, like the Sim Plus tool, all these videos are pretty high quality. It would seem unlikely that any viewer would be able to notice the difference between the baseline, main, and high files. So, and again, Sintel's the lowest, Talking Head is the highest, and the largest difference was with Sintel. So really, if you look at all these tests, they basically, at a high level, said the same thing. They basically said few viewers would notice the difference between the baseline and the high profile with any of these files. They all rated the Talking Head video the highest, the Sintel video the lowest, and the Haunted video in between. So what does that tell us about PSNR? So PSNR correlated 100% with every other metric that we applied in this particular case. And I'm not going to generalize it. It's going to work that way every time you try it. But I think, Netflix, as I said a few minutes ago, used PSNR for their per title analysis until 2016. PSNR is the beat bag of all the, everybody says PSNR is awful, very low correlation. We've seen scatter graphs to kind of prove that. And it's got some deficits. There's no tuning for specific playback devices. There's no attention weighting in the Moscow University tool. But in the land of the blind, the one-eyed man is king. And if all you can afford is PSNR, I think you get a lot of value from applying that metric to some of the compression decisions that you make. I mean, would I use the Techtronics tool if I had it to keep? Absolutely. But just because I don't have the perfect tool doesn't mean I'm not going to use a tool that can still give me pretty valuable information. And in my own practice, we talked about that I kind of considered myself a golden eye before because I've been looking at compressed video since 1992. But this is what I used to do. I would encode my videos, and this is when videos were 640 by 480. I mean, I tried this with a 4K video. And then I would bring them into Premiere Pro, put them on the same timeline, get the frames matched up, and then just go back and forth and look for, and that's only the still image side. That doesn't even cover motion artifacts. So I went from this to this, where I can have pretty graphs that show me which is the highest quality, which is the lowest quality, when the difference is greater than X%. I can see the difference map here. We'll cover what these tools are here. So, yeah, PSNR isn't perfect, but I think you can get a lot of valuable information from it. And that's what we're going to go for that's what we're going to cover for the rest of the session. Any questions so far?
Do these tests take into account audio?
Say it again.
Do these tests or tools take into account audio?
Sorry,
Audio.
Yeah, good question. So do we have any tools testing audio quality? Anybody have any? I don't have any, but anybody have a response to that? That's because I'm getting into a point where I need that, and I'll be looking for it. Next book, not this. Not this book, but.
Do you plan to talk about
The Netflix? No, because I didn't use it. I didn't have it's Netflix open source VMAF, which is a good thing and a bad thing. Basically, it means if you can compile it and figure out how to use it, you can use it. On the other hand, it's not in any easy to use tool yet. So you can't buy a tool and say, apply the VMAF algorithm. So I have not had a chance to use it.
What was your source on the 3 videos?
Say it again?
What was your source? What did you digitize?
Good question. So what was my source on the 3 videos? So the Syntel was, downloaded the movie, the highest quality iteration possible at 4K. Talking Head was a ABC HD video of me, and then Haunted was a DSLR 1080p source video. But they were all encoded into a mezzanine file format, so probably 30 megabit per second 1080p, which I think mimics what most studios are doing for their uploads. Okay, so let's see how I use this stuff. And one of the things, particularly with the Moscow University tool, the thing, it's nice to say that Psnr has value, but the thing that these tools allow you to do is not only measure the difference, but see the difference. So with objective quality metrics, I always say trust but verify. And that gets back to what I talked about with that difference in color. A slight difference in color would totally wreck your Psnr score. But if you look at the frames in front of you, you see, hey, nobody's going to care about that. So maybe I want to see if I can fix that, but I'm not going to stop using this encoder because it's not going to make a difference. And we'll see how the Moscow University tool really makes that possible. So the tools that I use most of the time are the Moscow University tool, VQMT, and the SimWave Video Quality of Experience Monitor, or SQM. And this is how the VQMT works. It's a $9.95 tool. You load the source file here. You can load up to 2 encoded files, which is amazing. If you're comparing 2 different encoding techniques or 2 different data rates, or you can load both files. You choose the metric. They support 20 metrics, PSNR, MSSIM, SSIM, and then you press process, and then it runs the test, and it gives you this results visualization screen. So what you're seeing here is 2 video files. The red was the first process, the blue was the second process, and you see the scores of both videos through the entire video. And this over here is the entire video, and this black area here shows the results in here. So you see a full view of the entire video, and then this black section here is down here. And you move through the video with the slider, and then when you see a frame that you want to look at, you click Show Frame, and then you see this frame. Okay, so this is the full frame at this point in the video, and I put time code in all my test clips, so that's not in the tool, that's in my test file. And then you can scroll through the original file, the compressed file 1, and the compressed file 2. So when I say trust but verify, I can scroll over to where there's, and we'll see it in a second, but I can scroll over to where there's a huge difference between these two. I can click Show Frame, and then I can see what the qualitative difference is between alternative 1 and alternative 2. So for me, Psnr is, again, it's not the best out there, but if I can visually verify what the tool is reporting, I think I get a lot of value out of that. What do we like about it? The video quality measurement tool, it's affordable, it's visual, multiple algorithms, and if you're interested in more about the tool, I reviewed it for Streaming Media about 1.5 years ago. It's a little bit of a pain to use. It only compares files of like resolution and like frame rate, so if you're comparing a 640 by 360 iteration to a 1080p original, you have to scale it up in FFmpeg. So that's a little bit of a work hassle, but it's doable. And then the scores, for PSNR don't really correlate to subjective perception. And it doesn't give you the ability to rate a video based upon the playback platform. SQM is the second tool. This is the $4,000 tool or the $3,500 tool. My review is here. It's based on the SSIM Plus algorithm. That's the next generation SSIM algorithm from the same inventor of the original one. Scores correlate, as we talked about before. You can predict results based upon device, and you can run on the command line or in the UI. Moscow University tool comes with a very useful command line as well. So I do most of this stuff via command line and then come in and report the scores. SQM workflow for the GUI is you load the test file here, the source file here. You choose which platforms you want to rate down here. Then you press the magic go button. And when it's running, here's the original file. Here's a difference map between what the original file or how the original file compares to the compressed file. And then here's the ratings for the devices that you selected. So you can kind of track it in real time. You see none of this in the batch process, of course. It's running in the background, and it just spits out a score. And here's what the scores look like. So this is a laptop. This, I think, is a 4K TV, another 4K TV, and this is a core score that always gets reported. So when it reports it in the CSV file, you know the mean score both for the overall test and for each device that you've decided to test. And then it's got a graphical results tool, so you can kind of compare the graphics over here. And then it also has the ability to compare files side by side. I don't think it's as flexible as the Moscow University tool for that kind of operation, but those features are available. What do we like about it? It's got a unique quality algorithm that has a lot of perceptual analysis in it. The scores correlate with viewer perception. If they say it's an 85, they're saying viewers will rate this as excellent. Supports multiple devices, multiple resolutions. If you're comparing that 640 by 360 file to a 1080p, you don't have to scale it up in FFmpeg. It'll do that for you. That's really nice from a disk perspective. And soon it should handle multiple frame rates as well. So if you wanted to, is the lowest quality iteration better at 40 by 270 at 15 frames a second as compared to 10 frames per second? Can't do that with any tool now. But I think at some point in the near term, they'll be able to compare those quality-wise. It's more expensive. The price is $2,400. And I don't think the tool is accessible from a visualization perspective. I don't find it as easy to use that way as I do the Moscow University tool. So how do I use all this stuff? The test that we're going to look at, I'm in the process of my next book. What I did for this book was I chose 8 test files of various types. Some are talking heads, some are high motion, some are movies, some are animation, some are screen cams, some are PowerPoints with video, because they're all different, right? And all videos encode differently. And then I went through all these tests that we're going to see for each one of those video files. And the test that we're going to discuss here, I produced most of the files in FFmpeg using the X.264 codec. They're all 720p files. Data rates are varied by video. I used 100%, when I wasn't testing for these configuration options, I used 110% constrained VBR, keyframe interval of 3 seconds, bframe of 3, and reference of 5. So that's kind of my base configuration for encoding. So which X.264 preset? Once you choose the profile, the next decision you have to make when you're encoding with FFmpeg or any tool that uses the X.264 codec is the preset. And what the preset does is it trades off quality against encoding time. So again, here's the test description that we talked about. And this is what I found. So there's 11 presets from ultra fast, super fast, all the way down to placebo. Red is the absolute worst score. Green is the absolute best score. And what's interesting is the average quality difference as measured by PSNR was only 8.13%. Okay? So 8.13% is probably in that, almost visual, not quite visual. I don't know how many people could pick up the difference. Certainly once you get beyond this one. So what does this tell you from an encoding perspective? Well, if you look at the time involved, what I'm doing here, again, there's an 8% average difference between the worst and the best. So if you spread that entire 8% over 100% valuation, and then you plot in the encoding time, so the blue is the encoding time, I'm sorry, the red is the encoding time, the blue is the quality, we see that here is probably the lowest quality that's acceptable. You wouldn't want to go anywhere south of this, and this I think is the very fast preset, gives you roughly, somewhere over 90% of that entire 8% at this preset with a very slow encoding time. You'd never want to go past here because the quality actually drops when you go down to the placebo. And the preset is kind of in the middle. So what does this tell me? If you're in a situation where you're at capacity, okay, you're encoding using the medium preset or say the very slow preset, and you're at capacity, and you're about to buy a new encoding tool and a new workstation to support it, then I would say, why don't you drop the preset to very fast. You get, again, 90% of the 8% quality difference, and you cut encoding time from here to here, which is probably, you're losing 60% of your encoding time, and from here you're losing a lot more. So sometimes you encode for quality, sometimes you encode for capacity. I would argue here, if you're using this preset and you're about to buy a new encoding station, I would drop it to here, and nobody's going to notice the difference. So it's not always about quality, it's about throughput and encoding efficiency. Keyframe interval, same analysis here. This is VQM, so lower scores are better. And I'm sorry, lower scores are better. I see a lot of people who came from the broadcast world encoding with one keyframe per second. Always drives me crazy because it is the worst possible quality. This slide kind of convinces them of that. If you are encoding single files, not adaptive bitrate, higher keyframe intervals do deliver higher quality. I've never gone as high as 20, but I've gone as high as 10. It's what I recommended before ABR technologies came into place. If you're doing ABR, you're going to be either 2 or 3 seconds, and you're going to lose some quality as compared to the highest possible quality here. But again, for most of these files, if you throw the screen cam and the animations out, there's not a huge amount of difference between the keyframe interval of 1 and 20. And it's really kind of funny because a lot of people will say, oh, a keyframe interval of 10 will give you, 40% better quality or 50% better quality. And if you actually do the work and compare the files, you see that the differences are usually a whole lot less. Reference frames, this is another, reference frames are frames from which the encoded frame can find redundant information. The trade-off is encoding time versus quality. What's the quality look like? Well, 16 reference frames will give you the highest quality in pretty much every encode that I tried in my average test files here. 1 reference frame is almost always the worst. But what's the difference in quality? The maximum difference was 1.28% for tiers of steel. What's the difference between 10 and 16 is 0.04. So why do I care about that stuff? Because the encoding time for 1 reference frame is 51 seconds. For 16 reference frames, it's over twice as much. So if you drop from 16 reference frames to 5 reference frames, you gain 43% encoding capacity at a loss of 0.3% quality. So again, it's not always about quality, it's about efficiency and affordability. And then this is a tough one, choosing VBR versus C. How many people use VBR in their encodes? What % constraint? Anybody? Nobody's state secrets here? Or, how many people use CBR religiously? Okay, so the quality difference between 2 pass, 1 pass is always the worst, 2 pass is the worst here, 200% is always the best. So yeah, VBR looks good from a quality perspective. It gets even worse for CBR if you look at the transient issues. So this is the results visualization tool in the Moscow University, or the interface. And what we see here, looking at the VQM metric, so higher scores are worse, we see a spike. And if we click on the frame, we see that this is the VBR frame, this is the CBR frame, and this 2 or 3 frame sequence is very degraded because the CBR encoding algorithm didn't have the data at that point to get a high quality frame. So what you see sometimes, not every time, with CBR is transient quality issues, meaning 1 or 2 frames or 3 or 4 frames will look very ugly as compared to VBR. The problem with VBR is deliverability. So this is a tool called Telestream Switch. This is CBR. This is VBR, and you can see the data rate varying over time. Which stream would you prefer to deliver over a cell connection or over any kind of constrained connection? So it's a little bit out of the scope of what we're talking about here today, but when you're looking at CBR versus VBR, there's 2 major issues. One is quality, and you need to look at both overall quality and transient quality, and VBR gives you the best of both, but deliverability is a huge issue. And there's a reference here to an article I did on my website that you can read all about that. And if you're using 200% constrained VBR, you lose a lot of efficiency, and you can degrade the quality of experience if you're delivering versus 200% constrained VBR as compared to CBR. So I don't recommend CBR. I don't recommend 200% constrained VBR. I recommend 110% constrained because you have a little bit better quality, you avoid the transient quality issues, and you produce a very deliverable stream of video. If we have time, we can kind of look at this, and I'll explain it in a bit more detail. Okay, so how do you use this information to build your encoding ladder? And this is kind of what Netflix came out with in December of 2015 is they came out with per title encoding. So they said, we're no longer going to use a standard encoding ladder for all of our videos because it's inefficient. You know, an encoding ladder is good for 1 video, right? And for low motion videos, it's probably too high a data rate. For high motion videos, it's probably too low a data rate. And they said, we're not going to use 1 anymore. We're going to use a custom encoding ladder for each video that we encode and distribute. So this is kind of this is kind of what I go through with my clients. It's kind of what I go through with my own videos. When I'm creating an encoding ladder, I choose the lowest rate for mobile. I say, how low do I want to go? And then I choose the highest supported data rate, and that's a cost issue. How much can my monetization support from a cost perspective? And then I choose a data rate of around 3 megabits per second. I want that to be a pretty high quality stream because if you look at Netflix publishes an ISP index every month, and if you look at the average sustainable stream for most of their ISPs that they report on, it's typically between 2.8 and 3.2 megabits per second. So I want a stream that's going to look good at that rate. And then I fill in the blanks going between 150% and 200%. So if I started at 200 kilobits per second, that's my low stream. 4.6 megabits per second, that might be my high stream. This is the targeted for the highest sustainable throughput, this guy over here. And then I kind of just run the numbers backwards. You know, so this is 200 and something percent, this is 200%, this is 1.6, this is, you know, around 1.33, this is around 1.5, and this is around 1.5 as well. Okay, so these are S10 encoding people, how they do it. They'd all come up with different numbers. There's nothing magical, but that's kind of the process I go through. And then the question is, we've chosen our data rate, so what's the best resolution at each data rate? So what Netflix does is they encode every file at a bunch of different resolutions at a bunch of different data rates. So they have and they started out using Psnr. They've since moved to the VMAF algorithm. And then they look at, okay, what's the highest of all the files that we encoded at 3.4 megabits per second, what's the highest quality? So our 4.6 megabit per second file will be a 1080p. Our 3.1 will be 1080p. Our 19 will be 720p, 720p for the 16, The 1 megabit per second file would be 540p. 500 kilobit per second is still 540. I'd probably move that to 360 just to have a file at that resolution. And then our lowest resolution file would be at 270, not at 180. So that's how they build their encoding ladder, by using objective quality metrics. And then this is kind of a cool graph. This shows you at any point on the data rate scale, you can see what the highest quality resolution is. So if you say, okay, if we want a 2.5 megabit per second file, the 1080p stream is the highest quality stream. And you can also see which streams are never the highest quality. So a lot of people have really low resolution streams in their encoding ladder, and what this tells you is these streams down here are never the highest quality, so you might as well just stop producing them. You're better off sending a 360p stream than a 270 or 180 stream at every data rate. And then you can also see how much quality goes up if you increase the data rate. So it's here, increases in data rate deliver a lot of additional quality. Here, the quality curve is starting to flatten out, which means less benefit for the higher data rate. And what happens when you move to HEVC, a higher quality codec? You get even more layers down here that never deliver the highest possible quality. So if you're moving to HEVC, you really don't need to include even your 640 by 360 stream, because 540 at all data rates will deliver a higher quality image than 640 by 360. And then this is SQM. This is the again, this is the one we talked about where scores between 100 and 80 were all excellent. So what I see with a lot of my clients is they have 1 or 2 or 3 1080p streams. The question is, do you need them all? How low can you go from a data rate perspective and still have excellent quality? That's what this graph is telling us. Zoolander was the highest motion clip, probably the hardest to compress that I had, and we lose excellent quality around 4 megabits per second. A lot of the others, you can go down to 3 megabits per second, 3.5 megabits per second, and still stay in the excellent quality range. So a lot of people have prophylactically high data rates at the high end because they want to make sure it looks good. But if you run this kind of analysis, and this is where you save your money, right? I mean, you don't want to check data rates at the 200 kilobits per second, because if you save 10%, you save nothing. On the other hand, if you can cut your top data rate by 25%, that can go right to your bottom line in terms of bandwidth savings. And what we're looking at here, this is kind of the argument for per title animation. If you run the SQM metric, you see that here I've got 91.48 score at 8 megabits per second. For an animated clip, I get the same score at 5.5 megabits per second. So if you're not doing per title encoding, you should consider doing per category encoding and encoding all your animated clips at a slightly lower data rate. What do you need to do all this stuff? You need a really fast computer. So this is, I've got an HP Z840. I think it's 40 cores. It's got SSD drives. And if you test on a real, a traditional hard drive, because you're doing so much converting and so much YUV and so much analysis, that disks make an incredible difference. And we see that this is the Z800, this is the Z840. The clock speeds of the processors here are relatively similar, but the disks here in the Z840 are all SSDs, and here they're traditional. And you see a very significant decrease in time from both the cores and the SSDs. So do you want me to go to my website and show you that QoS stuff for VBR, or do you guys want to punt and? Yes? Because I think it's fascinating. So the big question I always had, and I'm, as you probably know by now, I'm a really objective kind of guy. And if I can't prove it, I don't believe it. And a lot of times you don't know stuff until you have a tool that can help you actually see the difference. So what I did, I found a tool called Charles Proxy. Anybody, who here has used Charles Proxy? Anybody? So what Charles Proxy does is it lets you see the actual packets that are being sent from the server to the player. So what I did is I created this clip. It's 30 seconds talking head and 30 seconds ballet. So it's a mix of high motion and low motion. And then I encoded it using this encoding ladder. And I encoded it two ways, one 200% constrained VBR and one CBR. So this is what the CBR looks like. This is what the VBR looks like. So we see a huge swing in the different segments of the file as it related to whether it was talking head or ballet. So this is a nightmare if you're looking at CBR versus VBR because the packet sizes are going to be hugely different. And then I constrained it to different levels. So what you can do with the Charles Proxy, number one, you can, I'm going to move here. So what you can do is you can constrain it to different levels. You can say, okay, I want this video constrained at 3.2 megabits per second or 4.5 megabits per second. And what you see here are the various packets that are coming down. So we have different folders on the streaming server sending different segments, and you can track and record what's actually being sent. So it's a little bit, let me see if I can. So this is the CBR experience here on the right, and this is the VBR experience on the left. And this is for playing the entire file. Okay? So what observations can we make about the two experiences? Which one played more different layers? VBR. So VBR here, we see we had 4 layers that were played during the playback of this file. Here we see 2 layers. And we see the vast amount of the layers in the 2.1 megabits per second range. With the VBR, we see a lot at 2.1, but we also see a lot at 1.5. And we see a lot at 1.0, and then some all the way up at 3.1. And if we look at how the numbers work in this particular case, and this was played back the M3U8 file in Safari, to play the same video file encoded with VBR, I downloaded 49 segments, which means I downloaded a lot multiple times in different data rates. My overall bandwidth was 90.1 megabytes. For CBR, I downloaded 34 segments. The overall download bandwidth was 73. So the viewer looking at CBR watched 32 segments at 2100 kilobits per second, while the VBR viewer cycled through all the different data rates that you see over there. So if you're looking at overall quality of experience, you'd have to say that the CBR delivers a much more consistent stream, and in this case, a much more efficient stream. Lower data sent, higher consistency of experience in the packets.
And there was no network constraint, everything was played from the same machine?
Yeah. But and it was all same connection, same everything. So, all right, so any questions on anything that we covered?
What is causing these issues with the VBR?
What is causing this difference? What's causing it is that the packet sizes are very different for the VBR and the CBR. So if the packets takes longer to download, the player's going to say, holy cow, we have a problem. I need to switch streams. The CBR packets are very predictable, identical size. It can narrow in on an acceptable approach right away. But so if we start downloading the 3.1 megabit per second packets, that's going to be okay for a while during the CBR. But when the high motion packets start coming through that are bigger, it's going to take longer for them to come. The player's going to say, we have a problem. I need to switch streams. And if the problem is severe enough, it's going to cycle all the way down to here. And then it's going to say, well, life is good. The talking head segments come back. Life is good. Let's increase the quality. And then you start the cycle all over again.
So the problem is that the
Yeah.
adapted to VPL. So if you improve the client,
It's possible. And there is a session on that today that I'm going to go to. So it's a good point. I'll tell you after. I got to let people go and let the next people come in. But thank you for your attention.